Welcome! In this session, we will dive into LeetCode problem number 1597, build binary expression tree from Infix expression. We'll explore the problem details, analyze the requirements, and work through the solution step by step. Let's get started. In this problem, we are tasked with building a binary expression tree, or BET, from a given Infix mathematical expression represented as a string S. A binary expression tree is a special type of binary tree where each leaf node is an operand, such as a single digit or a variable, and each internal node is an operator, like plus, dash, asterisk, or forward slash. The input string S will be fully parenthesized, which means every operator will have its operands clearly grouped within parentheses. This makes parsing the expression more straightforward, as the parentheses explicitly enforce precedence. Your goal is to implement the function exptree that constructs and returns the root of this tree. As part of the implementation, you'll work with a node class, where each node has a value, a left child, and a right child. This forms the structure of the binary expression tree. The input to the function is a string S, which represents a valid infix expression. The length of S will range from 1 to 10,000 characters, and it will consist of digits, variables represented by single lowercase letters, and operators like plus, dash, asterisk, and forward slash. Parentheses are included to enforce precedence and group sub-expressions, so you don't need to manually figure out operator precedence. The output of the function is the root node of the constructed binary expression tree. For example, consider the input S equals 3 asterisk 4 dash 2 asterisk 5. The function should build a tree where the root represents the operator with the lowest precedence, and its left and right subtrees represent the group sub-expressions. The structure of this tree will ensure that the order of operations is respected. For the input S equals 3 asterisk 4 dash 2 asterisk 5, the binary expression tree would look like this. The root node contains the operator dash, which has the lowest precedence in the expression. The left child of the root represents the sub-expression 3 asterisk 4. And the right child represents 2 asterisk 5. Each of these subtrees is further broken down into individual operands and operators. Parentheses are implicitly added to the expression as open parenthesis 3 times 4 close parenthesis minus open parenthesis 2 times 5 close parenthesis to make the precedence clear. This ensures that the multiplication operations are evaluated before the subtraction. The tree structure reflects this precedence, with asterisk nodes as the children of the dash node, and their respective operands as leaf nodes. This hierarchical structure is what allows the tree to represent the entire expression correctly. Now, let's take a look at another example. Suppose the input is S equals 1 plus 2, asterisk, 3 to 4. The corresponding binary expression tree would have the asterisk operator as the root node because it connects two major sub-expressions. The left subtree represents the sub-expression 1 plus 2, where plus is the operator, and 1 and 2 are the operands. Similarly, the right subtree represents the sub-expression 3-4, where dash is the operator, and 3 and 4 are the operands. Since the expression is already fully parenthesized, the tree structure directly reflects this grouping. The root node asterisk ensures that the multiplication operation is performed after the addition and subtraction operations in its subtrees. Consider another expression, S equals A asterisk B plus C slash D. For this input, the binary expression tree will have the plus operator as the root node because addition has the lowest precedence among the operators in this expression. The left subtree represents the A asterisk B sub-expression with asterisk as the operator, and A and B as the operands. The right subtree represents the C slash D sub-expression with forward slash as the operator, and C and D as the operands. Parentheses are implicitly added to the expression as asterisk B plus C slash D to clarify the precedence and grouping. This tree structure ensures that multiplication and division are performed before the addition operation, maintaining the correct order of evaluation. To summarize, the input string S is guaranteed to be a valid infix expression that is fully parenthesized, so precedence rules are always clear. Operands in the expression can be either single digits or lowercase English letters, while operators are limited to plus, dash, asterisk, and forward slash. The binary expression tree must adhere to these rules, and the structure of the tree should reflect the precedence and grouping enforced by the parentheses. Some important edge cases include single operand inputs like a, which result in a tree with just one node, and nested parentheses like open parenthesis 1 plus 2 close parenthesis times open parenthesis 3 minus 4 close parenthesis, where the tree must correctly represent the nested hierarchy. Additionally, for very long expressions, the implementation must be efficient, ensuring the tree can be built correctly even when the input string is large. To tackle problem number 1597, which involves converting an infix mathematical expression into a binary expression tree, let's first consider a brute force approach using recursive parsing. The idea here is to identify the main operator in the expression, that's the operator with the lowest precedence that isn't enclosed within parentheses. Once identified, we split the expression into left and right sub-expressions around this operator and recursively apply the same logic to build the tree. However, this approach comes with significant challenges. Parsing strings recursively while accounting for parentheses can be error-prone. Furthermore, locating the main operator requires scanning the string multiple times, which results in high time complexity. This makes the approach inefficient, especially for large or complex expressions. In terms of complexity, the time required is O(n) squared, because of repeated scans, and the space complexity is O(n) due to the recursion depth. These drawbacks highlight the need for a more optimized solution. A more efficient strategy is to use the two stacks approach, which is an optimized method based on the shunting yard algorithm. This approach transforms the infix expression into postfix notation, or reverse Polish notation, and then constructs the binary tree from the postfix expression. Here's how it works: we use two stacks, one for operators and another for operands, which are the nodes of the binary tree. As we traverse the expression, if we encounter an operand, we create a tree node and push it onto the operand stack. For operators, we handle precedence and associativity by popping operators from the operator stack and building subtrees accordingly before pushing the current operator. Parentheses are managed explicitly, opening parentheses are pushed onto the operator stack, while closing parentheses trigger the popping of operators until the corresponding opening parenthesis is found. After processing all characters, any remaining operators are used to build the final tree. This method ensures correctness by adhering to precedence and associativity rules, and it processes each character efficiently. The time complexity is O(n), since each character is traversed once, and the space complexity is O(n), due to the stacks used. Ultimately, the two stacks approach is the chosen strategy for solving this problem because it is both efficient and robust. Unlike the recursive parsing method, this approach processes each character in a single pass and handles operator precedence and parentheses seamlessly. Its efficiency lies in eliminating repeated scans of the string, making it scalable for even the most complex expressions. Additionally, the structured nature of this algorithm makes it easier to debug and maintain. While it does require careful attention to precedence and parentheses, the trade-offs are manageable compared to the inefficiencies of recursive parsing. In summary, the two stacks approach offers the best balance between efficiency, correctness, and maintainability, making it the ideal choice for building a binary expression tree from an infix expression. The problem build binary expression tree from infix expression is all about converting a mathematical expression written in infix notation, like 3 plus 5 asterisk 2, into a binary expression tree. In this tree, the leaf nodes represent operands, such as numbers or variables, while the internal nodes represent operators like plus, dash, asterisk, or forward slash. The challenge lies in ensuring that the tree respects operator precedence and properly accounts for parentheses, so that the order of operations in the expression is preserved. To achieve this, we adapt the shunting yard algorithm, which was developed by Etzger Dijkstra. This algorithm uses two stacks, one for operators and one for operands, where the operand stack eventually forms the binary expression tree. The first step is to define some helper functions. For example, we need a function to assign precedence levels to operators. Plus and dash have the lowest precedence, while asterisk and forward slash have higher precedence. Parentheses require special handling to ensure proper grouping. Additionally, we define a helper function to construct nodes for our binary tree from the operators and operands we process. Now, we initialize the two stacks that form the backbone of our algorithm. The first is the operator stack, which stores operators and parentheses to help us enforce precedence rules. The second is the operand stack, which holds the operands and intermediate subtrees, eventually forming the complete binary expression tree. Once the stacks are ready, we parse the expression character by character. If the character is an operand, we create a tree node for it and push it onto the operand stack. If it's an operator, we compare its precedence with the operator at the top of the operator stack. While the top operator has greater or equal precedence, we pop it from the stack and construct subtrees using nodes from the operand stack, then push the resulting subtree back. Once that's done, the current operator is pushed onto the operator stack. For left parentheses, we simply push them onto the operator stack, while for right parentheses, we pop and process operators until we encounter the matching left parenthesis, which is discarded. This ensures that sub-expressions within parentheses are evaluated correctly. After parsing the expression, we finalize the binary expression tree. If there are any remaining operators in the operator stack, we process them one by one. For each operator, we construct subtrees using nodes from the operand stack and push the resulting tree back. When all operators are processed, the operand stack will contain a single element, the root of the binary expression tree. Let's walk through an example to see how this works. For the input 3 plus 5 asterisk 2, we first push 3 onto the operand stack as a tree node. Next, we push the plus operator onto the operator stack. Then, we process 5, pushing it as another tree node onto the operand stack. The asterisk operator is next, since it has higher precedence than plus, it goes onto the operator stack. We then process 2, pushing it as a tree node onto the operand stack. At the end of the expression, we pop asterisk from the operator stack, construct a subtree with 5 and 2, and push this subtree back onto the operand stack. Finally, we pop plus, construct the final tree using 3 and the subtree rooted at asterisk, and the result is a binary expression tree with plus as the root, 3 as the left child, and asterisk as the right child. This approach relies on key insights to ensure correctness. The use of operator precedence guarantees that operations like multiplication and division are evaluated before addition and subtraction. Parentheses are handled carefully to enforce proper grouping of sub-expressions. The resulting binary tree represents the expression structure, where each operator becomes a parent node and its operands or sub-expressions are its children. The algorithm is supported by two critical data structures, the operator stack, which helps maintain the correct processing order of operators, and the operand stack, which is used to build the binary expression tree step by step. From a complexity standpoint, the algorithm is efficient, with a time complexity of O(n), where n is the length of the expression, as each character is processed just once. The space complexity is also O(n), due to the stacks in the resulting tree. It's important to handle edge cases, such as expressions with multiple parentheses like open parenthesis 3 plus 5 close parenthesis times 2, single operands like 42, or nested precedence scenarios such as 3 plus open parenthesis 5 times 2 close parenthesis. These cases test the algorithm's ability to correctly interpret and construct the binary expression tree for various input formats. Here, we begin by defining a node class to represent each node in our binary expression tree. Each node will store a value, as well as pointers to its left and right children. Next, we define the solution class, which contains the exptree method. This method is responsible for constructing the binary expression tree from the given infix expression string. To manage operator precedence, we define a helper function precedence that assigns priority levels to operators, giving higher precedence to multiplication and division over addition and subtraction. Another helper function, buildTree, is used to construct a subtree by popping an operator from the operator stack, and then popping two operands from the node stack to serve as its left and right children. The newly formed subtree is then pushed back onto the node stack. We initialize two stacks, nodes to store tree nodes and ops to store operators. A while loop is used to iterate through the characters in the input string, processing each one based on its type. If the current character is a digit, we create a new node with that digit and push it onto the node stack. If it is an opening parenthesis, we add it to the ops stack. For a closing parenthesis, we repeatedly build subtrees using the buildTree function until an opening parenthesis is encountered, which is then removed from the ops stack. When an operator is encountered, we compare its precedence with the top operator on the ops stack. If the operator at the top has higher or equal precedence, we repeatedly build subtrees until this condition no longer holds, then push the current operator onto the stack. The loop continues to the next character in the string. After processing all characters, we ensure all remaining operators in the ops stack are resolved by building subtrees until the stack is empty. Finally, the root of the fully formed binary expression tree is the last remaining node in the node stack, which we return as the result. Here, we begin by defining a node class to represent the building blocks of our binary expression tree. Each node contains a value val, which can be an operator or operand, and two child nodes, left and right. In the solution class, the main method exptree takes an infix expression as a string and constructs this tree. To manage the process, we use two stacks, one for the tree nodes, called nodes, and another for operators, called ops. As we iterate through the input string s, we check each character. If the character is a digit, we create a new node with the digit as its value and push it onto the node stack. If we encounter an opening parenthesis, we push it onto the ops stack to handle operator precedence later. Now, when we encounter a closing parenthesis, we need to process all operators within the parentheses until we find the matching. To process the operators within parentheses, we repeatedly call the buildTree method, which we'll discuss soon. Once all the operators are processed, we pop the opening parenthesis from the ops stack. For any operator encountered outside parentheses, we compare its precedence with the operator on top of the ops stack. If the top operator has higher or equal precedence, we call buildTree to construct part of the tree. This ensures that the operator precedence rules are respected while building the tree. After resolving higher precedence operators, we push the current operator onto the ops stack. Finally, once all characters in the string have been processed, any remaining operators in the ops stack are resolved by repeatedly calling buildTree. The completed binary expression tree is represented by the single node left in the node stack, which we return as the result. To support this process, the precedence method is used to assign precedence levels, where multiplication and division have higher precedence than addition and subtraction. The buildTree method is responsible for constructing subtrees from the nodes and operators stacks. First, it pops an operator from the ops stack. This operator will serve as the root of the subtree being constructed. Then, it pops two nodes from the node stack, the right node first, followed by the left node. A new node is created with the operator as its value, and the left and right nodes are assigned as its children. This new subtree is pushed back onto the node stack, ready to be used in further tree construction. This method ensures that the expression tree is built correctly, following the rules of operator precedence and the natural left-to-right order of evaluation for infix expressions. To begin solving the problem, we start by initializing two stacks, one to hold tree nodes and another for operators. At the start, both nodes and ops are empty, and we set the index I to 0. As we process the input string, the first character is 3, which is a digit. We create a node with the value 3 and push it onto the node stack. Next, we encounter the plus operator. Since the ops stack is empty, we simply push plus onto it. Moving on, we process the next digit, 2, and create another node for it, adding it to the node stack. When we reach the asterisk operator, we check its precedence relative to the top operator in the ops stack. Since asterisk has higher precedence than plus, we add it to the ops stack without popping anything. After adding asterisk to the ops stack, we process the final digit, which is another 2. We create a node for this digit and push it onto the node stack. Now, we begin constructing the expression tree. First, we pop the asterisk operator from the ops stack and create a node for it. We then pop the top two nodes from the node stack and set them as the left and right children of the asterisk node. This new subtree is pushed back onto the node stack. Next, we handle the plus operator by popping it from ops and creating a node for it. Again, we pop the top two nodes from nodes and set them as the left and right children of the plus node. This results in the final tree, where plus is the root, with 3 as its left child and the previously created asterisk subtree as its right child. The tree structure is now fully built and matches the given expression. Now, let's look at the second example, where the input is open parenthesis 1 plus 2 close parenthesis times 3. We begin by initializing the nodes and ops stacks, both empty, and set the index I to 0. The first character is, so we push it onto the ops stack to mark the beginning of a sub-expression. Next, we process the digit 1. We create a node for 1 and push it onto the node stack. The following character is plus, so we push it onto the ops stack. Then, we encounter the digit 2. As before, we create a node 42 and push it onto the node stack as well. At this point, the node stack contains nodes 41 and 2. When we encounter the closing parenthesis, we know it's time to finalize the sub-expression. We pop the plus operator from the ops stack and create a node for it. The top two nodes in the node stack, 1 and 2, are popped and set as the left and right children of the plus node. This subtree is then pushed back onto the node stack. We also remove the from the ops stack since the sub-expression is now complete. Next, we process the asterisk operator and push it onto the ops stack. Finally, we handle the digit 3. We create a node 43 and push it onto the node stack, preparing to finalize the full expression tree. To finalize the tree for the full expression open parenthesis 1 plus 2 close parenthesis times 3, we pop the asterisk operator from the ops stack and create a node for it. The top two nodes in the node stack, which are the plus subtree and the node 43, are popped and set as the left and right children of the asterisk node. This results in the final tree structure with asterisk as the root, the plus subtree as its left child, and 3 as its right child. The tree accurately represents the input expression, with proper precedence and grouping of operations. In the third example, the input is 4 divided by open parenthesis 2 plus 2 close parenthesis. We begin by initializing empty nodes and ops stacks and set the index I to 0. The first character is 4, which is a digit. We create a node 44 and push it onto the node stack. Next, we encounter the / operator, which we simply push onto the ops stack. When we process the opening parenthesis, we add it to the ops stack to mark the start of a sub-expression. The following character is 2, a digit. We create a node 42 and push it onto the node stack. Then, we handle the plus operator by adding it to the ops stack. Finally, we process another 2, create a node for it, and push it onto the node stack. Now, we encounter the closing parenthesis, indicating the end of the sub-expression. We pop the plus operator from the ops stack and create a node for it. The top two nodes in the node stack, both 2, are popped and set as the left and right children of the plus node. This subtree is pushed back onto the node stack. We also remove the from the ops stack. To finalize the entire expression tree, we pop the / operator from the ops stack and create a node for it. The top two nodes in the node stack, 4 and the plus subtree, are popped and set as the left and right children of the / node. The resulting tree has / as the root, for as its left child, and the plus subtree as its right child. This completes the expression tree for 4 divided by open parenthesis 2 plus 2 close parenthesis. To analyze the time complexity of building a binary expression tree from an infix expression, we start with the traversal of the input. The algorithm iterates through the entire string, processing each character exactly once. This gives us O(n) for the traversal step. Next, we handle operators by pushing them onto the ops stack and using the buildTree function to process them. Since each operator is pushed and popped from the stack exactly once, this also contributes O(n) overall. Similarly, parentheses are managed by pushing and popping them from the ops stack, and since each parenthesis is handled only once, this step also adds O(n) to the time complexity. These combined steps ensure that the traversal and handling of operators and parentheses are all linear in complexity. After processing the input string, there's a post-traversal step where any remaining operators in the ops stack are processed. During this phase, the buildTree function is called to handle each operator. Just like before, each operator is processed exactly once, contributing O(n) to the overall time complexity. When we combine all these steps, input traversal, operator handling, parentheses handling, and post-traversal processing, the total time complexity becomes O(n). Moving on to space complexity, the first component to consider is the ops stack, which stores operators and parentheses. In the worst-case scenario, such as deeply nested expressions, this stack can grow up to O(n) in size. Similarly, the node stack, which holds node objects for operands and subtrees, also grows proportionally to the input size, resulting in an O(n) space requirement for this stack. The binary expression tree itself is another contributor to the space complexity. Each node in the tree corresponds to an operand or operator, and the total number of nodes is proportional to the input length. This means the tree takes O(n) space. Combining these components, the op stack, the node stack, and the tree itself, the overall space complexity of the algorithm is O(n). Whether in the best, average, or worst case scenarios, we always process every character in the input string and construct the corresponding tree, leading to O(n) time and space complexity across all cases. Even in complex expressions with deeply nested parentheses or long sequences of operators, the algorithm maintains linear efficiency. When comparing this approach to a brute force method, the differences become clear. A naive approach might first convert the infix expression to postfix notation, which takes O(n), and then build the binary expression tree from the postfix expression, also O(n). While the time complexity remains O(n), the brute force method requires additional memory to store the intermediate postfix representation, making it less space efficient. In contrast, the current algorithm constructs the binary expression tree directly during the infix traversal, eliminating the need for extra memory. Mathematically, this efficiency can be proven. Each character is processed only once, and operators and parentheses are pushed and popped from the stack exactly once, ensuring O(n) time complexity. Similarly, the space used by the stacks and the tree scales linearly with the input size, giving us O(n) space complexity as well. This direct and efficient approach is a significant improvement over the brute force method. When constructing a binary expression tree, there are several common mistakes to avoid. First, ignoring operator precedence is a frequent issue. Operators like multiplication and division have higher precedence than addition and subtraction, and failing to account for this will result in an incorrectly structured tree. To prevent this, you can use a precedence map to determine when operators should be pushed to the stack or processed. Next, parentheses are another area where errors often occur. Parentheses dictate the order of operations and must be handled carefully. For example, opening parentheses should always push to the operator stack, while closing parentheses should trigger popping operators until the corresponding opening parenthesis is encountered. Lastly, some may attempt to build the tree directly without using stacks. This approach often leads to confusion and incorrect results. Using two separate stacks, one for operators and one for operands, or a structured single stack ensures that the construction process remains organized and accurate. Now, let's address a few more pitfalls and key insights for interviews. Off-by-one errors are a common source of bugs when traversing the tokens in the input string. It's easy to accidentally skip the first or last token or mishandle edge cases like single number expressions. To avoid these issues, verify that your traversal logic processes every token in the input. Another common mistake is assuming the input expression is valid. While LeetCode guarantees valid input, real-world applications often involve malformed expressions, such as ones with unbalanced parentheses or invalid operator sequences. Validation ensures robustness in these scenarios. For interviews, it's also important to demonstrate a strong understanding of stacks, especially for managing operator precedence and parentheses. Clearly explain the role of each stack when discussing your solution. If time allows, optimize for clarity. Consider starting with a recursive approach, which may be easier to explain, and then iterating to improve efficiency. Be sure to discuss edge cases, such as empty strings or deeply nested expressions, and explain the time complexity of your solution. Typically, the algorithm runs in O(n) time, where n is the length of the input, since each token is processed only once. Additionally, this problem connects to several related problems that can help you deepen your understanding. For example, LeetCode number 227, Basic Calculator 2, focuses on handling operator precedence, while LeetCode number 224, Basic Calculator, emphasizes evaluating expressions with parentheses. If you're interested in extending this further, LeetCode number 770, Basic Calculator 4, introduces parsing for polynomials. Finally, LeetCode number 889 explores tree building logic in a different context, constructing binary trees from pre-order and post-order traversal. As for alternative approaches, a recursive solution is often easier to implement and explain but may use more memory due to the overhead of recursive calls. Alternatively, you could use a single stack with structured nodes. This reduces the need for separate operator and operand stacks but requires careful management of node states. Another option is to use the shunting yard algorithm, which aligns well with compiler design principles. However, this method may be unnecessarily complex for simpler problems. Lastly, direct tree construction without intermediate stacks is possible, but it's significantly harder to implement and debug, especially when dealing with operator precedence and parentheses. Each approach has its trade-offs, so choose the one that best fits the problem's requirements and your comfort level. Great work! We've successfully tackled LeetCode problem number 1597, build binary expression tree from Infix expression. Remember, this problem is a fantastic example of how data structures like stacks and binary trees come together to solve real-world challenges. Keep practicing and refining your skills. Thank you for watching, and don't forget to like and subscribe for more coding tips. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!